Okay, so welcome to the lesson on work and power. So we'll quickly highlight our outcomes here. So we have a few here, and these are mainly going to be yellow. Recall work as a measure of the mechanical energy transferred, because it says recall because work was part of the Science 10 curriculum. Recall power as the rate of doing work. And then describe power qualitatively and quantitatively. So we're going to make that green. So what I'm actually looking that you're able to do to show me you can meet those outcomes is calculate any variable in the work formula, which is force times distance times cos theta. Equate the area under a force versus displacement graph to work. Define power. Calculate any variable in power is equal to work divided by time. Relate system international units, so that should be just units without the extra E in it there, not unites, to physics quantity, so powers in watts or in joules per second or in Newton meters per second, and state the work energy theorem. So that's yellow. Okay, so moving right along. Remember, you can stop and start this. You can fast forward as much as you need to, rewind as much as you need to, look for the stuff that's new. So energy is the ability to do work. In the last lesson, I described energy as the ability to change an object or its environment. That's the same thing as the ability to do work, because that's what that really translates into, is the ability to change an object or its environment. Work, then, is a measure of the amount of energy transferred to or from an object. So a measure Okay, so work is a measure of the amount of energy transferred to or from an object when a constant force is applied over a given distance. That constant is actually kind of a weird one. When we're using a formula, it has to be a constant force. If we're actually going to use the area under force versus displacement graph, then it can be a changing force. And that'll come up again when we talk about the graphs. So there's three different ways that we're going to define work, and that we can, three different things we can do to determine how much work is being done to an object. So the first one is the basic, it's the formula. Work is the product of the force applied on an object and the object's displacement, which leads to this formula. Work is equal to force times distance. So that should be familiar from last year. W is work. Okay, and that's measured in joules, just like energy is. Because remember, work is like a measure of the amount of energy, so it's measured in the same units as joules. F is the constant force, so the force applied. Remember, and that's measured in newtons. And D is the displacement of the object in meters. And this formula we use when we have a situation where maybe, like, if we have a free body diagram where we have a force that acts horizontally or, say, vertically, but it acts in one direction. So that's our force. And then where the displacement of the object is in the same direction or in the same plane. So it's either going to be in the same direction or in the opposite direction, like that. That is when we use this particular formula here, and then this formula is on your formula sheet. We have other situations, though, that we've talked about with forces. So if we have a situation where we have a free body diagram, but let's say the force is applied at an angle. So that's our force, and it's at an angle in here. Let's say there's some sort of angle in there. But we still have our displacement is still in one of the planes. Right? Like the displacement is still kind of either in the horizontal plane or the vertical plane compared to that at an angle. If that's the case, so if F is applied at an angle, then this is the formula. Work is force times distance times cos theta. This is actually the formula that's on your formula sheet, right? This formula here is not on your formula sheet directly. It's just that when you have a situation like this, then theta is equal to 0, right? And sine 0 is just 1. You can also define work as a change in energy. So the work done on an isolated system means no friction, equals the sum of the changes in EP or EK. We'll say and or EK. So what that leads to is what's called the work energy theorem. And this is a pretty big theorem in physics, because what it says is that work is equal to a change in energy. So it says that work is equal to a change in energy is equal to work. So essentially work and energy are interchangeable in formulas. This is on your formula sheet. As a formula, it's also on there as physics principle number 3. And what you want to remember here is that change in energy is going to be energy final minus energy initial. The other way of finding work, so we can find work with just a strict formula with force times distance, or force times distance times cos theta. We can find work by finding a change in energy, if that's the information we're given. Or we can find work by finding the area under a force versus displacement graph. And this looks a little bit different for a constant force versus for a changing force. So we'll deal with the constant force first. And if we have our graph, if we have a constant force, then our force versus displacement graph, so this would be force versus displacement. Then that graph, a constant force means that force occurs at some number of newtons, and it never changes. So this is newtons and meters. So constant force means you've got a horizontal line, and then you're just finding the area underneath that horizontal line. That will give you work. So work is equal to the area under, which in this case would just be length times width. This idea that area under a force versus displacement graph is equal to work is not on your formula sheet, so that's a relationship that you need to memorize. Back up there. So then if you have a non-constant force, the graph will look a little different. And there's different, this graph can actually look, this is just one example of what this graph can look like. There's other ways that this can look. But basically, it means that your force, the graph of force, is changing. So it's not a horizontal line. It's going to be a straight line that's either increasing or decreasing. I'm just going to put V versus D here, or sorry, F versus D here. So an example of a non-constant force might be something like this. where that value is increasing. So then the work is equal to the area under. So if you know the formula for the area of a trapezoid, you can use that, or we can split this into two, right? We've got two shapes here, really. We've got like a triangle, which I can call A1, and a rectangle, which I'll call A2. So work is equal to the area under, which is going to be equal to the area of section 1 plus the area of section 2. So in this case, base times height over 2 plus length times width. Or whatever it is that you have and however you organize that. Now that's just always going to be in the way, isn't it? Okay, let's go down here with that. Now we can have different types of work. We can have positive work, we can have negative work, and then we have situations where no work is done. So we're going to look at each of them. Positive work is done when the displacement and force are in the same direction. So this would mean that the angle between force and displacement is equal to 0 degrees. Or you have a diagram that looks like this. Oh, excuse me. So there's my free body diagram with my force, and my displacement is in the exact same direction. So there's no angle between them. The angle between them is equal to 0. When you have positive work being done, the force that's providing that work, or that's causing the work to be done, the force will increase the speed of the object. Increase the object's speed. Another way that you can think about that is that energy is added to the object. So examples of that would be things like pushing a book across a desk. So pushing a book across the desk. You're adding energy to the object by applying a force. The book is moving in the same direction that you're applying the force, so that's going to increase the object's speed. Another example is dropping a ball. In that case, it's the force of gravity that is adding energy to the object and increasing the object's speed, because you're dropping the ball. Negative work is pretty much the exact opposite of everything I just wrote there. It means your displacement and force are in opposite directions. So the angle between displacement and force is 180 degrees. So you have a free body diagram, or you have like a situational diagram where you've got maybe the force is being applied to the right, but the displacement of the object is in the opposite direction. In this case, the force will decrease the object's speed. And that's because energy is being removed from the object. So a couple examples of this are like braking in a car. So braking while driving. You're applying a force of friction backwards, but your displacement's still forwards. The car slows down. Energy is removed. The kinetic energy decreases. Or thinking about vertical motion, this would be the throwing an object in the air. So throwing a ball in the air. The ball is moving upwards, right? That's a displacement of the ball, but the force of gravity is actually acting down on the ball. They're acting in opposite directions, and that slows the object down. Then we have situations where there's no work being done. And this occurs when the displacement and force are perpendicular to each other. So this means that when the angle between displacement and force is 90 degrees, then that means no work is being done. So an example of this would be I'm applying a force upwards on an object. Maybe that's the normal force I'm applying upwards, but the object has a displacement to the right. So the force will not change the object's speed, or the force does not change the object's speed. And there is no change in the energy of the object. So examples of this are carrying an object while walking. So if I'm carrying a book while I'm walking around the classroom, my hands are applying a normal force to the book, okay, but I'm not changing the object's speed, because the force I'm applying on the book is upwards, but I'm walking forwards, which has an angle of 90 degrees between them. So that the no work is being done. That doesn't mean your arms aren't going to get tired. Like your arms your muscles have to work in order to do that, but there's no work being done on the actual object. Another time when no work is done is when an object is moving with uniform circular motion. And that's because the displacement of the object with uniform circular motion is always perpendicular to the force that's towards the center of the circle. Okay, so now we're just going to do a bunch of examples. So we have a few situations here where we just want to find the work done in each situation. So whether it's using a formula, whether it's using the work energy theorem, or whether it's finding the area under a force versus displacement graph, we are finding the work done. So a boy pushes on a crate with a force of 42 newtons, making the crate slide forward 12.9 meters. So we have a force of 42.0 newtons and a displacement of 12.9 meters, and we want to find the work done. So work is equal to force times displacement, which is just 42.0 newtons times 12.9 meters. Pretty simple and straightforward. So 542 joules of work is done in that situation. A 36 kilogram object is lifted straight up with a constant speed through a height of 3.9 meters. Okay, and we want to know the work done here. So there's a couple ways we can approach this. We can look at the fact that work is equal to force times distance. Okay, but in this case, if you're lifting something up, then the work that is being done is against gravity, so that force becomes the force of gravity, or m times g, and the d we can leave as d, or we can put it as height. So basically what you're finding is the change in gravitational potential energy, where we have 36 kilograms times 9.81 meters per second squared times a height of 3.9 meters. Which gives you 1,377 joules, or with sig digs, 1.4 times 10 to the 3 joules. You could have also approached this as work is equal to a change in energy, which is the final potential energy minus the initial potential energy, where that first, what you basically have is m times g times h minus 0. Okay, so you end up with the same thing. Okay, a person pulls a box with a force of 76 newtons on a rope that makes an angle of 30 degrees to the ground, and the box moves a distance of 12.7 meters. So we want the work done in that situation. So work is force times distance times cos theta, which is 76.0 newtons times 12.7 meters times cos 30 degrees. I think on a previous part of the slide I said sine 0 is equal to 1. That's not correct. It was cos 0 is equal to 1. I mixed up my trig ratios there, so just ignore that part. And this gives us 835.9 joules, or with sig digs, 8.4 times 10 to the 2 joules. And moving right along, we have a graph, a force versus displacement graph. I'm missing my title, but that's F versus D. So an object is moved by a force according to the following graph. So we have a graph here that has two sections. So we've got a triangle like this that has a base of 20 meters and a height of 110 newtons. And then we have a rectangle that has a height or a length or a width, whichever one you want to call that, of 110 newtons, and then it's got a base there of 65 minus 20, or 45 meters. Okay, so this, we can find area 1 here and area 2, and work is equal to the area under, which is equal to area 1 plus area 2. So in this case, that's base times height over 2, and then we're going to add length times width. So 20 meters times 110 newtons divided by 2 plus 45 meters times 110 newtons, which is 1,100 joules plus 4,950 joules, which we can just write as 6,050 joules, and I won't worry too much about changing that for sig digs. Okay, then we also have to work with situations where we have to rearrange the formula to find a different variable. So we want to find the mass of an object that is lifted vertically through 12 meters by a force that results in a transfer of energy equal to 165 joules. So sorry, that's change in energy, which is also equal to work. And we're looking for mass. So we've got a change in energy. Work is equal to change in energy, which in this case is equal to the change in gravitational potential energy. Okay, so we have height is equal to that change in energy. Mass is what we're looking for. Mass is equal to change in energy divided by g times h, which is 165 joules, divided by, and you need big brackets on the bottom, so you have to find 9.81 meters per second squared times the height of 12 meters. Figure out what that is first before you divide by it to get 1.40 kilograms. Force of 16 newtons is applied to an object, causing a transfer of 241 joules of energy, and we want to know, sorry, that should be change in energy. We want to know how far was the object moved. So work is equal to force times distance. So remember, this is equal to work. Change in energy is equal to work. So distance is equal to work divided by force. So I'm kind of dispensing with my vector symbols there. So that's 241 joules divided by 16.0 newtons, which equals 15.1 meters. Okay. try a couple different ones here. We have, if a 985 kilogram car is traveling at a speed of 12 meters per second, how much work is required to stop it? So we want to know work, which is, remember, is equal to a change in energy. We have a mass of the car of 985 kilograms. We have an initial velocity of 12 meters per second, and we want to stop the car. So that means our final velocity is 0 meters per second. So work is equal to a change in energy, and in this case it's going to be a change in EK. So it's EK final minus EK initial. So 1/2 mvf squared minus 1/2 mvi squared, which is 1/2 times 985 kilograms, in this case times 0 meters per second squared, minus 1/2 times 985 kilograms times 12.0 meters per second squared. So it's 0 minus 70,920 joules, or negative 7.09 times 10 to the 4 joules. So that's a case where the work is negative because the car's moving forward, but you're applying the brakes to stop it, which means the force you're applying is in the opposite direction of the displacement of the car. So we'll try a similar one, but where we have our VI and VF are kind of switched around. So we want to know what work is done. So what work is done, or what's the change in energy for a 10 kilogram object to get it to accelerate from rest. So we have an initial velocity of 0 meters per second, and we want it to get to a final velocity of 2.25 meters per second. We're given a distance, but we actually don't need that distance at all. Oops, that should be meters. So again, what we want is a change in energy, which is EK final minus EK initial. That EK initial is just going to be equal to 0 because our initial velocity is equal to 0, so we can just leave that out, and we just want 1/2 mvf squared, which is 1/2 times 10.0 kilograms times 2.25 meters per second squared. Okay, and that gives us 25.3 joules, right? So it's minus 0 joules, minus 0 joules. Okay, and now a question that requires us to do a little bit more work here. We want to know how, sorry, no pun intended, how much work is done on an 8 kilogram wagon rolling along a flat sidewalk if we have an applied force of 60 newtons that acts opposite to its direction. So we're going to make that force negative, and it brings it to a rest in a time of 2.0 seconds. So we have VF is equal to 0. We don't know what VI is. Okay, that's all the stuff that we know. So what we want to get to, because we're trying to find work, we don't have enough information to do change in energy because we have no idea what initial velocity this object's traveling at. So we're trying to get to being able to use work is equal to force times distance, where we have negative 60 newtons as the force, but we don't know what our distance is. So if we back up a bit, we have an applied force. So that means we have a net force. That's the only force that's acting on this. So if we draw a free body diagram, and we make forward positive and backward negative, we have a force acting on that object backwards to that. That F applied is backwards, it's 60 newtons. So what that means is F net equals F applied. So mass times acceleration equals F applied, and acceleration is equal to negative 60 newtons divided by the mass of 8 kilograms. So that gives us an acceleration of negative 7.5 meters per second squared. Once we have acceleration, we can use displacement is VF delta t minus 1/2 a delta t squared to figure out the displacement of the wagon, and then we can use that to find work. So this is 0 minus negative 15 meters, or just a distance of 15 meters. which we can then plug into our formula up here, negative 15 meters. And what that gives us then is negative 900 joules of work is done. I'll just leave that as negative 900, not bother about the sig digs for that. Okay, next concept, and this is very much related to work, is power. Okay. And power is just the rate of doing work. And when we have a rate, a formula that's a rate, what that means is that the formula is work divided by time, because that tells us how much work we can get done per second. Okay, power is measured in watts, okay, named after James Watt, who invented the steam engine. Work, W is work or energy, that's measured in joules, and time, T is time, and that's measured in seconds. So with the work energy theorem, this can be written as change in energy over time. It means the same thing. Okay, and this is on your formula sheet. This version is with work over time. Work is equal to a change in energy is also on your formula sheet. And a watt is equal to a joule second. Okay, so 3 quick examples here with power. An electric motor is used to lift a 55 kilogram stack of bricks to a height of 6 meters in a time of 8 seconds. We want to calculate the power output of the motor. So power is equal to work over time, which is equal to force times distance over time, which when we're talking about vertical motion, that force becomes the force due to gravity, or work becomes gravitational potential energy. They mean the same thing. You can look at it however way you're comfortable looking at it. So that becomes 55 kilograms times 9.81 meters per second squared times the height of 6.0 meters, and then we're going to divide that by 8.0 seconds, which then gives us a power value for power here of 405 watts, or 4.0 times 10 to the 2 watts. It actually ended up being actually 404.7, so that would be 4.0 times 10 to the 2 watts if you wanted to do that for scientific notation. Okay, example 8. Remember, I am going through this pretty fast because I'm trying to make the video a little shorter than the last one. Don't know if that's going to work, but you can stop and start it as much as you need to. Okay, so similar situation here. A 60 kilogram student runs at a constant velocity up the incline shown below, and that takes a time, to the right, that takes a time of 4.5 seconds. We want to calculate the power output of the student. So what you need to recognize is the only, this is the height. This distance here doesn't actually matter if we're not doing force times distance. We're doing the change in height is what's important here. So we have a height of 2.5 meters. So we're basically using the same process we used in the previous example, mgh over t. So that is 60 kilograms times 9.81 meters per second squared times a height of 2.5 meters, and then that's all divided by the time of 4.5 seconds, which gives a power output of 327 watts, or 3.3 times 10 to the 2 watts. Okay, and one final example. 1.00 times 10 to the 3 kilogram car, or 1,000 kilograms, which is easier to write, it accelerates from rest to a velocity of 15.0 meters per second in a time of 4.00 seconds. And we want the power output of the car over that time interval. So power is equal to a change in energy over time. In this case, it's change in kinetic energy over time, which is EK final minus EK initial over time. So 1/2 mvf squared minus 1/2 mvi squared divided by time. So 1/2 times 1,000 kilograms times 15.0 meters per second squared. That initial kinetic energy is going to be 0 because the initial velocity is 0, so it's just minus 0 joules, and then that's all divided by 4.0 seconds. And what you should get there for an answer is 28,125 watts, or 2.81 times 10 to the 4 watts. Okay, so your things that you can work on, or practice questions you can work on if you want to practice the stuff if you don't remember it from last year. Page 163 to 170, numbers 1 to 21. Page 173 to 174, numbers 1 to 7. Page 175 to 176, numbers 1 to 5. And page 187 to 190, numbers 1 to 16. And then there's some reading you can also do on work and power, and that's page 32 to 34.